In this video, we do simple considerations on the Laplace transform, starting from the Fourier transform. In particular, we define the Laplace transform in terms of the Fourier transform. So we take the Fourier transform of a certain function that I call x of t. So it's a function of the variable t, and I call it x of t. And then I multiply this function by an exponential e to the minus sigma times t. So sigma is a real quantity, it's a real number, and we define this to be the Laplace transform of the function x of t. So by definition, this is written in terms of a Fourier transform, so we have an integral from minus infinity to plus infinity, and sometimes for specific signals, you might see the lower bound of the integral to be 0 minus. So that's called the unilateral Laplace transform, whereas from minus infinity to plus infinity, this is called the bilateral transform. Usually the Fourier transform is defined as a bilateral transform, whereas the Laplace transform is usually defined as a unilateral transform. Now I will not get into the technical details here, but in general, when we have a certain signal, usually the signal starts at x or t equal to 0. In this case, let's think of t equal to 0. You have some kind of initial time here, where the function starts at 0 and then it changes. But before t equal to 0, so for t less than 0, the function is usually thought to be 0. For example, this is actually an example, and therefore it makes sense that in this case the transform from minus infinity to plus infinity is like a transform from 0 to infinity, because the function before time t equal to 0 is 0. Therefore we can actually start the integral at 0, from 0 to infinity. But let's not get into these kind of details here. So we have the function, which is x of t multiplied by e to the minus sigma t. And then we have the usual exponential e to the minus I omega t dt. So this is a Fourier transform, but now we can put these two exponentials together. So we can put them together, integral from minus infinity to plus infinity, x of t, and then I have e to the minus sigma plus I omega t dt. And we can define sigma plus I omega as s, and s is a complex number because you can see that it has a real part equal to sigma and an imaginary part equal to omega. And this transform can be denoted in the following fashion. So this is equal to x hat of s. So we have the variable s, and remember that s is a function of sigma and omega in general. So actually the result of this integral is a function of both sigma and omega. So it is a function of the real part of this number and also the imaginary part. So we might as well write the result as a function of the entire complex number s. And this is equal to this Laplace transform of x of t. Now we can use the inverse formula for the Fourier transform, because we have defined this as a Fourier transform. We know the inverse transform, the inverse Fourier transform and the Fourier transform, and in particular we take them for granted. So from here we can reconstruct the signal x of t multiplied by e to the minus sigma t, because this is the signal, if you want, that we have here. This is equal to the inverse transform from minus infinity to plus infinity of this object here, x hat of s, and then we have e to the I omega t d omega divided by 2 pi. So this is how we can define it. And now I can multiply both sides of this equation by e to the sigma t, so I can get rid of this factor. I have x of t equal to integral from minus infinity to plus infinity x hat of s e to the sigma plus I omega t, Then I have d omega divided by 2 pi. Now let me multiply the denominator by the imaginary unit I, and let me of course multiply the numerator by I, and let me put I inside this differential like this, and I can also rewrite this differential as d of sigma plus I omega, where in this case the variable is omega, so sigma is kept constant, it is a constant. And we have to be careful because in this case the um, the boundary of the integral should be written properly in the following fashion. So in this case, since the variable is sigma plus I omega, and I can call that S, the integral is equal to integral from sigma minus I infinity, or if you want, we can put capital T, and we can consider a limit here. So we take the limit as capital T goes to infinity, because that's what's going on here. We have this object, this variable, which we call S, and we integrate over this variable S, and we integrate from sigma minus it to sigma plus it, x hat of s, e to the st ds divided by 2 pi I, and this is exactly the definition of the inverse Laplace transform. And in particular, let me mention that when you have the inverse transform, sometimes it is convenient to calculate this as a contour integral. So it is possible to, since you can see from the definition that we are integrating basically over a certain line from minus I infinity to I infinity, and we have a real part which is non-zero, so we are integrating from sigma minus I infinity to sigma plus I infinity, and somewhere here we have the real part equal to 0. I mean, the real part of sigma could be either positive or negative actually, but for reasons of convergence, we could say something more on that, but I'm not going to do it here. And sigma is a real quantity, so the real part of sigma is equal to sigma. And then you can think that you can close this contour some way. And I mean, in some cases this is useful because you can use the residue theorem to calculate, to evaluate the complex integral. And this is useful when, for example, the integral along the semi-circumference goes to 0 due to the theorem that you have in complex calculus. So you have an integral over a certain curve gamma, x hat of s, e to the st ds over 2 pi I, which is sometimes convenient to evaluate the inverse Laplace transform.